Thank you. So, good morning. It's an honor for me to be here. My name is Casanueva, and I am an astrophysics PhD student at the Pontificia Universidad Católica de Chile. Today, I will present the work that I have been doing in the company of Patricia Tisera and Nelson Padilla about the physical origin and structural impact of star-gas misalignments. And this study was done by analyzing data from the CIELO simulation. So first, I will start with some context. In recent years, the advent of integral field unit surveys such as SAMI that provide spatially resolved spectra for galaxies has allowed the determination of the rotational axis of stars and cold gas, and hence the measurement of this position angle offset between both rotational axes. So for example, here we have data for one SAMI galaxy. On the left panel, we can see the H alpha velocity, which traces the star-forming gas component, and the stellar velocity on the right panel. So from this, we can get the rotational axis of these two components, which correspond to these black lines. And you can see that both components are not rotating with the same axis, and in fact, these are pretty misaligned. And despite most observed galaxies have their cold gas and stars aligned, there are a non-negligible fraction of galaxies in which stars and cold gas are misaligned. And this leads to the question, is the existence of misalignments expected by the current theoretical models? And studying this is relevant since if we find that the theoretical models can reproduce misalignments, we can interpret from them the causes of these star-gas misalignments. So, what does the current theory tell us? Well, according to lambda CDM, galaxies forms from the condensation and the cooling of the initial gas cloud within the dark matter halos. And since stars are formed from rotating gas, the natural assumption is that stars will inherit their dynamic characteristics, resulting in a coherent rotation. So in this regime, the tidal torque theory explains the origin and evolution of the angular momentum. But after the decoupling of the proto-halo region from the general expansion of the universe, these components might decouple due to nonlinear interactions. So we cannot use TTT anymore to understand the origin of misalignments. And some observational and theoretical studies have been done to understand star-gas misalignment, and they suggested that possible misalignments origins are galaxy mergers, continuous accretion of cold gas through the cosmic filaments, and interaction with nearby galaxies. However, this is still a problem not wholly solved, and most of these studies are statistical and don't study all the processes involved during the evolution of the galaxy with high resolution. Then our project aims to carefully analyze the evolution of individual galaxies over short time intervals with high resolution to understand the cause and impact of misalignment in the galaxy's histories. So through this, we aim to clarify how part of the galaxy population might be becoming misaligned and what imprints may leave the misalignments in the galaxy's structure. And we were able to do this detailed analysis thanks to the data from the CIELO project. These are zoom-in simulations that assumes a lambda CDM cosmology, and the subgrid physics includes a multi-phase model for the gas component, metal-dependent cooling, star formation, and supernova feedback. These multi-phase and supernova feedback models have successfully reproduced a galaxy's star formation activity during quiescent and starburst phases. And in a nutshell, what we did was analyze 5 central galaxies, 4 from local group analogs and another one with another environment. So we rotate separate components and calculate properties at each redshift with the per particle information to study the origin and impact of misalignment between cold gas and stars. So to illustrate what we did with each galaxy, we will talk about the evolutionary history of this galaxy, which has a spiral structure at redshift 0. So here we have the evolution of different properties of the galaxy as a function of redshift. In particular, please focus on the first panel, in which we can see the evolution of the angle between the rotational axis of stars and cold gas. And as you can see, there is a region shaded in pink where both components are considerably misaligned. So we studied in detail the interactions that this galaxy had and the origin and fraction of accreted gas at each redshift. And we conclude that this misalignment is due to gas accretion from the filament and from satellite galaxies that enter misaligned with respect to the disk of stars. So in this plot, we can see the angular momentum orientation and particle distribution at redshift 2. And as you can see, at this redshift, stars and gas are aligned, but there is an unbound gas here in green and satellite gas here in red that are misaligned with respect to the disk of stars of the central galaxy. And lately, that misaligned gas will be accreted, producing a misalignment. Later, that misaligned gas begins to form stars and strengthening a counter-rotating disk in the central galaxy. And after the misaligned gas have been mostly consumed by star formation, the galaxy accretes a gas from a merger, here in red, that enters aligned with respect to the disk of stars, so that the gas and the stars of the central galaxy end up aligned. And something quite interesting is that these misalignments may have imprints on the galaxy. So here we can see the mass distribution in radius and in height of star particles formed from gas particles with different angular momentum offsets. So in this study case, the counter-rotating gas forms stars in the innermost part of the galaxy, while the rest of the misaligned gas forms a thick disk. And to put some numbers, here we can see the fate of the mass distribution of the gas particles that are misaligned at redshift 0.85. And as you can see, at redshift 0, roughly 55% of the misaligned particles have already formed stars that remain in the central galaxy. And from this star, roughly 81% are established in a counter-rotating disk at redshift 0. And as I told you before, we did this type of analysis for 5 galaxies. And here we can see the case of another galaxy that, like the previous one, at redshift 0 has aligned stars and gas, but at redshift 2.45, both components were misaligned. So in this case, contrary to the previous case, the accreted misaligned gas particles dominate in mass and therefore dominate the galaxy's angular momentum. So stars formed from these misaligned gas particles will be located mostly in the co-rotating disk of the galaxy. So here, in the fraction of mass in orange. So, to summarize, we conclude that galaxy mergers and accretion of unbound gas can generate misalignment or alignment depending on its angular momentum orientation with respect to the stellar component at the accretion time, such as they can produce a torque on the pre-existing gas depending on the relative mass of accreted gas. Also, if the galaxy lost the dominant misaligned gas component due to stellar formation, and the galaxy receives gas accretion of aligned particles, the galaxy, gas, and stars might realign. And finally, of the 5 galaxies studied, 4 of them have gas and stars aligned at redshift 0. However, they did present misalignments during their evolutionary history, which left fingerprints in their structure, as for example, the formation of a thick disk or a counter-rotating disk. So thank you very much. Comments or questions are very welcome. And here is my email if you want to contact me for something.
Thank you. So have questions? Hi, very interesting talk. I have maybe 2 questions that are probably intertwined. The first one is if there's a certain star to gas ratio that is sort of preferential for these misalignments, and if the misalignments actually provoke a sort of star formation burst.
Yes, we studied the relation between the mass of gas in the central galaxy related to the mass of accreted gas, but we didn't found any threshold to determine that from this fraction of mass the galaxy components will misalign or not, because it depends. It's dependent on the. Sorry, maybe I have a plot that
Sure.
I get to clarify. But basically, it depends on the evolution of the galaxy after the accretion. In some cases, the star formation will be higher, and in that cases, these misaligned gas particles will be lost because they will form a counter-rotating disk, for example, as in the case that we saw. But in other cases, these misaligned particles will stay around, and they will affect the dynamics on the galaxy.
Yeah, thanks.
Thank you.
More questions? Okay, from Luis Enrique.
Hello, can you hear me?
Yes.
Okay, thank you, Catalina, for your presentation. It was very interesting. I was just wondering about, have you ever tried to, well, how difficult it is for you in these simulations to measure the angular momentum of the dark component? And if you have ever tried to do some kind of relationship between the alignment between the stellar component, the gas component, and the dark matter component?
Yes. In fact, we at some point analyzed the angular momentum of dark matter particles because we have that data, but we focus on the relation between angular momentum of gas and stars. So maybe it will be interesting, but for example, no, maybe we need to delve into that.
Yeah, okay, thank you.
Thank you.
Thank you. Okay, and let's thank the speaker again.